Hi, my name is Richard. I'm also with the relativistic heavy ion group. I'll be talking about something similar, which is jet analysis using energy correlators. I think Lily gave a really good introduction to jets, so hopefully everybody here is like an expert now. But like, if you have questions, I can answer them later, and or preferably like Lily answers them. So yeah, I guess I'll just jump right into it. So energy correlators are these like observables that were introduced by a group of theorists, including Yale Physics Department's own Ian Moult. So up here I have like a theoretical definition, which is the first two lines. And they were originally kind of thought up to measure something called like energy flow at a fixed angular distance. And that's sort of what this delta function here does. I'll explain like the RL in a little bit more detail. And this is a rather scary definition. So luckily we have like an experimental definition that's a little bit more tractable for studies in our detectors, which is just filling a distribution weighted by particle PTs. And I'll get into a little bit more detail about like the combinatorics and how we actually fill these distributions later on. But yeah, there's like a very nice geometric representation for this. So RL here stands for the longest side, or like the longest side in this R phase space. So if you remember from Lily's presentation, we kind of talked about these coordinates eta and phi. You can think of like R as like the Euclidean distance in this space, or it is like the Euclidean distance in this space. I think there's a question about like why we use like eta. I think like one of the answers is so we're studying relativistic like events. Eta is Lorentz invariant, I think. So that's, you know, maybe one of the reasons. And the way we actually fill this distribution is we'll compare like n particles in our jet. And then we have this factor, which is just the product of these transverse momentum over this term, which is like the nth power of the transverse momentum of the jet, and we'll fill it to the longest side in the R space. If that didn't make sense, I'll explain it better later. So my analysis focused on the n equals 2 and n equals 3 case. And you can think of like, sort of, I was mentioning this RL as a distance. You can think of it like actually like a polygon. So this is the n equals 2 case. And in this case, we have like two particles that we're comparing. And so we only have like a one-sided polygon. And it scales like n choose 2. So the n equals 4 case is actually a little bit inaccurate. There should be like 6 edges because we would compare these as well. Yeah. And sort of the reason why we care about these energy correlators, there are a couple of reasons, which are on the next slides, because they have a lot of nice properties. But one of the cool kind of like applications of this is that we can use it to probe something called the strong coupling constant, which is this fundamental, like, it's not really a constant. It depends on the energy scale, but like, yeah, it determines like the strength of the strong interaction that Lily mentioned. And by taking the ratio of these correlators that I'll show you later, we can actually find that they're directly proportional plus some like higher order correction terms. And this is another way that we can kind of extract this fundamental thing. Okay, yeah. So properties of correlators that makes them nice. One of them is IRC safety. So in detectors, there's this thing called linear and infrared safe. And this is like, so this is something that we care about in that we kind of like want our observables to have, just because basically in a particle collision, we can have a lot of soft emissions, and we can also have a lot of collinear emissions. Collinear just means like a particle emits like two particles that are sort of closely parallel. And these are actually not like resolvable by our detectors, or they're hard to resolve. So it's not a unique property. Like the specific type of correlator that I'm working with, which is called the projected correlator, is derived from something called a standard energy correlator. And it actually inherits this property. But if you want like a better idea, there are some like very outdated and none of these are used. But like, for example, if we just consider like the number of particles in a jet, this is obviously not like infrared safe, right? Because we have like soft particles that are affecting this number. Or like beyond like a trivial example, if you talk about like the leading momentum fraction of like the highest momentum particle in a jet, divided by the sum of particles, this is also not IR safe because the denominator is affected by soft particles. Another thing that's like an important, or I guess like one of the primary reasons we talk about like a projected energy correlator, rather than the standard energy correlator, which I mentioned earlier, is this like problem with dimensionality. So like this is the definition of a standard energy correlator. And so you'll notice like, or maybe you remember, back in the definition of like the projected correlator, there is this delta function that kind of filtered out the maximum distance. And I mentioned that it scales like n choose 2. So if we were to use this like standard definition, once we go to like n equals 4, we would actually need like a 6-dimensional plot. And also there's like this thing with data where as you go into higher dimensional like space, you get like sparsity in your data, which also like in terms of practical considerations makes it difficult to do analysis. So yeah, so I guess for a little aside, the crux of my project is kind of studying these energy correlators. But one of the problems that I was concerned with this summer was this thing called jet matching. So yeah, this is like a key complication in detector studies. So I guess like for a little bit of an explanation, a theorist definition sort of relies on QCD perturbative calculations, and they define jets and they kind of study jets using this definition, which includes uncharged particles. But in detectors, we have difficulty like getting the kinematics of these particles. And obviously those feed into like the definition of our correlator and how we calculate them. So we kind of want like a mapping between these two definitions. And it'd be nice like, and so like part of my project was building up this dictionary. Yeah. Okay, another tangent. This is sort of the like simulation pipeline that I used. So I use the same thing as Lily, which is Pythia. This is this Monte Carlo event generator. And these are sort of the jet definitions that I use. So the full jet, you can kind of think of as corresponding to like a theorist definition, which includes charged and uncharged particles. And then I have two definitions for charged jets. One, which is like sort of what you would expect to get from a detector, which is using only like what we measure from charged particles. And then another one, which is like a reconstructed charged jet, where I just strip out all the uncharged particles from this first definition. And then all of these feed into analysis. And this was like an iterative process that I had a lot of help with. So I guess this is like an interesting problem just because like naively, you would not expect sort of this jet matching to be one-to-one. And in fact, we figured out that it's not. So you can sort of like imagine if you have an algorithm that's clustering jets, if you have like sort of particles that are close in the space that are all charged, you might get like 2 charged jets per full jet, or like you might get some weird clustering where you get like 1 charged jet per 2 full jets, or the ideal case where you get 1-to-1. And so the algorithm that we ultimately it's a work in progress, but the algorithm that we ultimately settled on is we first cut based on the jet axis. So if they're less than 0.1 in the space, and then we cut on PT fraction to get our jet matching. Yeah. These are some of like the statistics that we get. So you can see like using our algorithm, it's quite a selective cut. If you start with like full jets and the number of charge jets, which you have less of, the sort of fraction that pass our jet matching is quite low. So we exclude a lot of jets. And yeah, maybe one thing in the future that we could work on is sort of trying to like get as many jets matched as possible. So it's a cool little optimization problem, I guess. This one's kind of boring. It's like a jet spectra. So this is like a matrix of like charged jet energies versus full. Yeah, and so you can see that like naively, we would expect the charge jet energies to be lower just because we stripped out a lot of the particles, and in fact it is. These are the correlators themselves. So I mentioned like the filling process from before. These are using Alice parameters. And this is sort of the EEC, so the n equals 2 case I was talking about for the 2-point correlator. And then this is the n equals 3 case. And I guess like the major sort of sticking point right now, or like, it's a work in progress. One of the cool things that came out of this, which is probably wrong, is that from our two charge jet definitions, we get like the same distribution for the correlator. And so like naively, we would expect them to be quite different. It would be really cool if they were the same, because that would just mean like, if you were a theorist, you could take like a full jet and kind of strip out all the particles to get a charge jet, and that's what we measure in experiment. But yeah, like it's probably wrong, but it'd be cool if it was right. And then this is the ratio, and sort of as I mentioned before, this is what we hope to eventually be able to extract the strong coupling constant from, and this is also like a work in progress that I'm currently working on. Yeah, in terms of future directions, I want to like examine correlators above n equals 3. The combinatorics gets a little bit complicated in these cases, but it's been implemented before. And then obviously, as I mentioned, extracting the strong coupling constant. And so that will sort of take me from, instead of working with simulations, to working with like actual data from probably Alice, I think, or a detector experiment. Also, I want to tune the jet matching and maybe alter the algorithm a little bit. And then also move beyond proton-proton collisions, which is also what I'm working with right now. Sorry, I forgot to mention that. Yeah.
Any questions, Rich? Yes.
Good, great presentation. Can you go back a couple of slides? I just had a quick question about the difference between the charge jet from full, one more forward.
Yeah.
No, the other direction.
Oh, sorry.
Yes, and the charge jet from charged constituents, are they identical? Like I can't tell from here if the points are.
Yeah. So it's hard to tell. So this is like one of the reasons why this is like such a annoying issue, is that like they're not exactly the same. Actually, for higher like R, they're statistically like different if you look at the error bars. Which is strange. Yeah. But if they were like identically the same, it'd be nice, because then I would know I'm wrong. Yeah.
Okay.
Maybe you said this and I missed it, but I didn't hear it. In the next slide, very next one.
Yeah.
Cole Z plot.
This one?
The Cole Z plot. One more forward. Yeah, that one.
Yeah.
So why is it like without any actual jet knowledge, it's very like cut off on like an XY slope. Like everything above that is like not there. It's all below that. Why is that so?
Probably to do with the parameters I set in the simulation. So there's like jet energy cuts that you can, or jet PT cuts that you can set.
These are matched jets.
These are matched jets, yeah.
Yeah, then it's not really possible for a charged jet that's matched to a full jet, if they are the same jet, to have more energy than the full jet, because full jet is charged plus.
Oh, are you saying why it's diagonal?
Yes.
Like, oh yeah. So like this sort of like, you see no entries here. Like naively, if you think about it, like I take a cake, I take out like maybe like 1/3 of the particles are uncharged, right? I take out like a slice of your cake, you're gonna have less cake. I don't know, that's a bad analogy, but yeah.
No, that makes sense.
Yeah.
Great. Last question. Seeing none, thank you.
All right.